What's up, people out there on the internet? You three that are watching this in the future. Maybe three. All right, in part 3 of the nervous system notes on 1072, let's go through the nerve impulse transduction or conversion again, which basically means you're going from a nerve, like a sensory cell, and you're moving through the neurons toward the CNS, or you're sending a signal from the CNS and it's going out to some type of effector cell, one way or the other, okay? And what are the effector cells?
They're like muscles or glands.
Muscles or glands, good. So it's going one way or it's going the other way. But in this step, remember, these neurons are not connected to one another. And if you look at 1072, the top left, that second paragraph, read that for us. Go, Sarah.
Once released, the neurotransmitter diffuses across the synaptic cleft, the gap that separates the presynaptic neuron from the postsynaptic cell. Diffusion time is very short because the gap is less than 50 nanometers across.
Yeah, so that's like a thousandth of a millimeter. So it's a very, very, very small space here. Keep going.
Upon reaching the postsynaptic membrane, the neurotransmitter binds to and activates a specific receptor in the membrane.
Okay, so I mean, you got a very, very small gap in between this cell and another neuron, or in between this cell and some type of gland. Okay, so let's go through the process real quick here. So a signal has been sent down a neuron. It's reaching the end of the axon. Number 1, Katie.
In the book or in the notes?
Notes.
Depolarization of an axon terminal membrane. The nerve impulse hits terminal cell membrane.
Okay, so terminal means the end. This depolarization, this action potential has sent a signal down to the end of the axon. Number 2, Mason.
Voltage-gated ion channel open up the ion terminus to allow calcium ions to rush into the cell because of the terminal membrane getting hit by the electrical impulse.
Boom, you get hit by electrical impulse. All right. So, signal reaches the end of the axon. Ion-gated channels open up. Calcium ions flood in. Number 3, Tay.
Calcium ions push the synaptic
Vesicles.
neurotransmitter.
Okay, so basically, calcium floods in, and the calcium is moving these vesicles to the axon terminal membranes, pushing them toward there. Remember, the vesicles are made out of a phospholipid bilayer. They're going to fuse with the bilayer at the end of the membrane. Number 4, they're going to release their neurotransmitters into the gap between the two cells, and the neurotransmitters are going to diffuse across the gap. So they're released on one side, they move from high to low, they're going to diffuse across the other side. Number 6, Mariah.
The neurotransmitter binds with protein receptors on the postsynaptic neuron or effector cell membrane.
Okay, so the neurotransmitter makes its way across, and it's going to bind the receptor proteins on the other side. Number 7, Walker.
The sodium floods in. No. The binding causes the receptor proteins, which may be a sodium chemical gated channels, to change shape and open.
Okay, so in the instance of, let's say, the signal's being sent down from one axon to the other, it may open that channel up, the neurotransmitter. Remember, sodium was kind of like, it was propagating along down the axon, kind of flooding and spilling over from one section to the next down the axon. And then when that channel opens up on the next neuron, some of that sodium starts to flood in, and then number 8, sodium floods in, depolarizing the postsynaptic membrane, meaning a signal is sent. You got an action potential that's sent along the next neuron. Number 9, Miranda.
Cholinesterase will break down the acetylcholine, causing the receptor proteins to close back.
Cholinesterase is what?
An enzyme.
And it's breaking down the acetylcholine. And so everything has to get back and reset the way it was in order for another signal to be sent along down the neuron. Super. Just super. 1073 at the bottom. So what does it take to actually stimulate a signal to go along here? So there's a couple of different ways we can reach threshold or maybe not reach threshold. The first one, excitatory postsynaptic potential. Excitatory means
Excited.
it's exciting, just like this lecture. Good. All right, so it has the ability to generate a new nerve impulse. Inhibitory, what does that mean?
To stop or slow.
Yeah, it stops or slows it from happening. So this is the inability to generate a nerve impulse, or it helps to turn it off. So you could have either one of these things working. So you could have a bunch of different nerve signals being funneled into the dendrites of the next neuron. And then is there enough of a stimuli to cause an action potential to send that signal down the cell? Okay, so on 1073, let's look at these graphs and see if we can figure out what's going on here. Yeah, let's look at part A, and you don't really need to know each one of these terms so much. I mean, you need to know excitatory and inhibitory. Oh, let's summation. What is that? 5 in the notes.
Yeah, okay. This term refers to adding dendrite stimuli together to reach the threshold potential in the cell body. Think of the following example, and this is into one area.
Okay, so this is the adding summation of that dendritics, the signals that are coming into the dendrites. Okay, so on part A, subthreshold, no summation. Now, do we have excitation in part A? Are y'all looking on part A at 1073? The picture? The graph at the bottom?
No,
Bless you.
we don't.
We don't have any excitation?
Yes.
Well, we have a little bit, but like
Okay.
not so much as the
All
other.
right, so there was some excitatory, but there's not enough for what?
Threshold.
No summation, meaning they happen like separately. So they're not, summation really means you can kind of like add their stimulation together. Okay, since they're so far apart, like you can think the x-axis being time there. Since they're so far apart, it's not enough to reach the threshold in order for an action potential to be sent. Good. In part B, temporal summation. Let's see. If you read up there, produced nearly simultaneous by different synapses on the same postsynaptic neuron. That's not it. On some occasions, the paragraph on the bottom left of 1073, two excitatory postsynaptic potentials occur at a single synapse in such rapid succession that the postsynaptic neuron's membrane potential has not returned to resting potential before the arrival of the second one. When that happens, the ESPS add together the effect called temporal summation. And so basically in the second one, those two are added together enough. And the same thing really happens in part C. It's just how they're added together. One's getting added together in the same spot, and then another, in part C, two are getting added together in two different places. So you're having two excitatory stimuli, okay, either one. And both, they're going to get added together enough where they reach the threshold. Both of them there's enough of a stimulus to send a signal, in other words. And then in part D, the summation of ESPS and ISPS, where you can see the red arrows coming in there in the cell body. You've got an excitatory stimuli, but you've also got an inhibitory stimuli. And when you add those together, they basically what?
Cancel out.
Cancel each other out, so there's not enough to reach threshold and send the signal along. Okay? So I wouldn't spend too long on that part. Neurotransmitters are ligands in the human body, things that affect the nervous system or neurons. And they can be sent to, or where neurons connect or to other glands or muscles. So the first one there, probably the one you're going to hear the most about because we're going to cover it tomorrow in part 4 of the notes. No, hold on, that's not right. Part 5 of the notes, sorry. Acetylcholine. Read 1 and 2 for us, Ashlyn.
Most common, this is mostly for making muscles of the PNS contracts.
Okay, so since we're talking about muscle contraction tomorrow, then acetylcholine is pretty important in that process. Okay, that's the neurotransmitter that's going to trigger those muscle cells. Number 2, in the CNS, it can be excitatory or inhibitory, depending on what's going on there with the signals. The next one, and don't spend a lot of time going through and memorizing all these. These are just some for you to become familiar with, some you may have heard of, and really just kind of talk about what their function is. The biogenic amines are talking about large amino acid chains, so almost kind of like a small protein, basically. Epinephrine, norepinephrine, these are produced by the same gland, the what gland? You might know where epinephrine comes from? Adrenaline? The adrenal gland, good. Speeds up body functions such as breathing, metabolism, heart rate. Norepinephrine assists with speeding up body functions. So they basically kind of work together. These two are called your fight or flight response. When that tiger comes through the back of the room and attacks Ashlyn, and we all see her getting mercilessly eaten back there, and we take off running. Who knows? How many of y'all would try to fight the tiger off?
I mean, I'm pretty brave, I probably would.
I doubt it. You'd probably be in shock and you'd be eaten next. I think that's why.
think that you just have a tiger back there and you need to get it off your chest, but this is the only way you can get it out. Is just by asking us what we would do.
What? Yeah, so a couple years ago, maybe a year ago, there were these two guys biking through the Washington State wilderness somewhere, and a mountain lion came out, attacked. Did you hear about this? Attacked one of the guys. His buddy took off running, so he was trying to get help. Okay. Well, the mountain lion's attacking the one guy, and so the guy that was on the ground managed to kind of to fight it or hit it or something, and it left and took off after his buddy who was running away, and it jumped him and got him down. The one that had already been down on the ground was hurt. He then like kind of limped off and he went to get help, and when he got back, his buddy that had previously run off, the mountain lion was sitting there eating him. So yeah, it's a valuable lesson learned, Walker. What would you do if your buddy was, I mean, can you imagine running off? I mean, it's not like a tiger that weighs 500 pounds. A mountain lion's probably like 120 or something. I mean, it could still kill you, but I mean, I feel like I could pick up a stick and get a good lick in or something. I mean, especially if it's sitting there like eating my buddy, like whack it over the back of the head as hard as you can. You got a bike, throw the bike on it. What are you doing with your life? Running off? Did he deserve to die? Make sure you edit this out. These are all value judgments that we have to make. Dopamine. I'm sure some of y'all heard about that. We got into quite the discussion this morning about Oregon legalizing hard drugs. I don't know what your particular thoughts on that. I'm not going to go political.
What do they legalize?
Hardcore drugs, heroin, cocaine, methamphetamines.
Like, did they
Decriminalize it. I mean, I don't guess you'd say legalized, but they decriminalized.
Okay, so not like recreational use.
No, I don't guess you could say they advocated recreational use. I think if you get caught with it, you're supposed to either pay like $100 fine or they're supposed to get you help with your addiction. Now, we'll see how well that works out for them. Do what?
You said meth too, right?
Meth, crack, heroin, no criminal, and these are small amounts. You still can't sell it and stuff, Katie. These are like small amounts, so just your average run of the mill, methamphetamine people carry around with them. Do what?
It's not side hustle.
This is on video, Katie. I mean, like, okay. I mean, the idea was they're going to get people help that are on drugs and get them off of drugs. I don't know if everybody on drugs wants to get off of drugs, to be honest with you. You got to be able to make that decision. Dopamine. Speaking of drugs, dope. Yeah. This is your happy neurotransmitter. Y'all know the rest. Serotonin. This is your sleep neurotransmitter. I think they make some kind of artificial version of this that people take when they're having trouble sleeping. People up in Alaska and Canada, all that sunshine in the summertime, what do? You know what you do? You take your mask. You can do this when you're driving on the road too. And you're not getting good sleep. Well, if you can't have nighttime, you have to make the nighttime. So all you and just like it's beautiful. It's like it's nighttime. You sleep. I mean, it's like a multi-purpose tool right here. Amino acids, small amino acid chains. GABA are inhibitory neurotransmitters. Neuropeptides. I think I talked about this the other day. Those are the ones that different neuropeptides cause you to feel that feeling of love that you have for someone special. Sarah. Some like substance P relays pain stimuli. Endorphins. How many of y'all like to run? Man, here like to run? No, because running's horrible and it makes you feel bad and your legs hurt, and I don't know why anybody likes to run. But some people that like to run, they run enough where they get the runner's high. Have y'all ever heard of this?
Yes.
Where they go past the feelings of pain and agony, I'm sure that that they have to feel, and they get past that point. These block substance P, and they're responsible for your second wind. I used to run in high school for track, mainly to get out of school, because we'd go to these track meets and but I wasn't fast, so I'd always have to run like the mile, the 2 mile, 800, and I never got the runner's high. I did throw up quite a few times running that distance, so maybe I was just on the precipice of being there. But anyway, heroin and morphine drugs mimic these neurotransmitters. They block that pain. Block the pain, take it away. All right. And gases. Y'all have heard of nitric oxide? Your friendly dentist, we get put under to get your wisdom teeth taken out. Was that somebody in here who's getting their wisdom teeth out?
I'm getting mine out on the 21st.
No, you have fun with that. They're gonna put you down, and then you see all these funny videos of people coming back too after they've been out of it. It's delightful. Carbon monoxide. This is an inhibitory neurotransmitter. Inhibitory meaning it kills you. Carbon monoxide is really bad for what purpose? Why is it bad?
You don't know you're getting poisoned.
Yeah, usually just what? You just get sleepy and go to sleep, and then you die. Your blood cells have a greater affinity for carbon monoxide than they do for oxygen. So even if you're breathing air that has oxygen and carbon monoxide in it, your blood cells are going to grab a hold of the carbon monoxide, and then you're going to go to sleep and probably die. A family out in Tuscaloosa, I think out toward Coker, 3 or 4 years ago, died. They had a heater going in their house, and it wasn't properly ventilated, and I think it was one of those like small propane heaters or something. And somebody found them all dead like the next day. I remember reading about this family up north. Somebody came into the basement. They drove in the basement and they unloaded some groceries, and they didn't turn off the car for whatever reason. And somebody found them all dead the next day, because the carbon monoxide had built up and kind of come up through the house. So proper ventilation, especially if you have any kind of like natural gas, is super duper important. I would recommend getting a carbon monoxide detector, because you go to sleep and die, but I'm sure nobody wants their entire family to die because they left their car on. My wife did that one time and almost killed all of us. We had this Corolla. I don't know what she was doing, probably on the phone. She had the car running, and I guess it was not loud, and she closed the door on one Saturday and left the car running for like 5 hours in the garage with the door closed. I guess luckily enough, probably the garage had a little ventilation or air coming through the cracks, and I guess the door maybe had a tight enough seal where not much got in. Did she do it on purpose? She'll never tell. Part 4, turn over to chapter 50. Your senses. All right, y'all turn over to 1101. Imagine you lean in to kiss that special person next to you, and this is what you see. That's how moles feel every time they go to kiss somebody. I don't know. Maybe they find this attractive. Who knows? What do you think, Katie? Would you kiss that? You just imagine all those little extensions just like moving independently of one another. Whew, that is one weird looking nose. Looks like a nose that somebody stuck a firecracker in and just split it open. All right. That's enough for the internet today. Let's see. Previous concepts. There are different types of energy in nature. Ligands cause a conformational shape change, and the signal transduction pathway is how a stimulus is converted, amplified, and then a response given to that stimulus. So we're going to go through some different senses here. For those of you at home, I posted a sensation video. I think it talks about some different ones. Crash Course has a sense video for like every one of your senses and takes you through the physiology of that if you want to know more about that, because we don't have time. But they're definitely good, those Crash Course videos with Hank. Sensation, what is that, Walker?
This term refers to an action potential that has reached the brain and sensed the nerve impulse.
Okay, so you had a stimuli, you sent something, that signal was sent to your brain. Perception, Mariah?
This term refers to the integration, thinking about it, of a received action potential.
What's the saying about perception? Let's say you and someone else experience the same stimuli. Would you have the same perception? Not necessarily, no. The whole saying is perception is reality. So what you see, perceive is your reality, right? Whether it's necessarily the same for someone else. It may be like, crazy people who like pickles. Like, pickles are disgusting. I couldn't choke down a pickle if my kid's life depended on it. Because it's just horrible. I would throw it up and gag every time. But some people like pickles. Like, what's wrong with them? But it's the same thing. So we have this different perception in our brains of like what that is, what the taste is. Look at Mason back looking around for a pickle back there. Okay. So perception is reality. This is another reason why eyewitness accounts, for those of you who want to go in criminal justice or whatever, are really horrible, because people perceive things and it's not necessarily what is there. Yeah.
I think we watched it in A+ or something, but it was after like the Abraham Lincoln assassination, and
Yeah.
they got like eyewitness accounts from like everyone in the room, and they said like none of them matched up, even though like everyone watched the same thing happen.
Yeah.
Like everyone heard him say something different, or they saw him come on and like say something different, like John Wilkes Booth.
Yeah.
And it was just like weird.
Yeah. Eyewitnesses are not reliable and very often. I like to think of back home and around Alabama, you hear these constant reports of Black Panther sightings. Yeah, like Wakanda. And so there are no, and a lot of people say, well, I saw a mountain lion and I saw a Black Panther. And really, the only large cat that's anywhere around here is mountain lions. There's some Florida panther, which is basically a subspecies of, Florida panther is a subspecies of mountain lion. And there's some mountain lions been spotted in Arkansas and Tennessee and kind of sporadically throughout the Southeast. I don't think there's been any confirmed sightings in Alabama of one since the mid to late 60s when somebody killed one, last one that's been around for a while. And so, and then people think they see a black one. And there's no scientific evidence whatsoever of any type of melanistic mountain lion. Like, there's not any. It's not like jaguars where like a fourth of them are melanistic. They are like mostly black, and you can kind of see the patterns underneath. There are none that I have found or that were out there. And so I swear, I got relatives, I got friends back home, they're all the time like, I saw a Black Panther. And I'm like, there is no such thing as a Black Panther. What are you doing going back to drugs? Anyway, so I think it's just somehow their perception. They're seeing something and they've heard these tells so often that they're like, that's what it's got to be. I'm like, don't y'all think when there's like 4 million rednecks running around Alabama and every one of them's got a game camera out in the woods, that at some point when they catch everything that you could possibly imagine on a game camera, if there was a panther, black panther, or even a mountain lion running around, that it would be on there. Like, wouldn't that make sense? I mean, like, I've seen tons of bears on game cameras throughout Alabama, and nobody ever sees a bear out hardly. So, I mean, it just blows my mind that they think they're out there. Now, one day, maybe somebody will find one and I'll eat crow, but I think the reality is they're seeing something and their perception is Black Panther. I had a cousin of my dad's, I guess she's my cousin, but an older one. She's like, I saw one come up to my back porch and eat my cat food. And I'm like, are you sure it wasn't just a black cat? Like a kitty? And she's like, no, it was big. Like, it was huge. And I'm like, okay, I don't even know what to say. I'm like, just set a camera out. What, you can take a picture of that? Nobody's ever seen one or had one on picture and you just couldn't take cameras and you was out there watching it out the back window?
Do you tell them that? You just let them think.
What?
Do you tell them that?
Yeah, I'm like, why didn't you take a picture? Or what? I mean, I'll say, like, you know, if you saw one, why is no one never on camera? You got 14 game cameras around your property. All right, stimuli. Stimuli is external energy. The reception is, so there's got to be a certain amount of stimuli or threshold for that to reach, to be for that signal to be sent to your brain. Amplification occurs on the way to the CNS. Transmission along the axons is saltatory. We already talked about that. Integration into the CNS. Perception occurs to determine the appropriate response. You know, if we see Ashlyn back there getting attacked by a tiger, we're going to perceive that stimuli. We're going to see things flying everywhere. Are we going to go back there and help her out, or are we going to run? These are decisions you need to think about ahead of time, because this could happen. It happens in, you know, Bangladesh. You ever heard about those tigers that, like, attack fishermen and stuff? People will be, like, fishing in these canals and stuff, and, like, tigers will come out of the woods and just, like, in the water, grab them, boom, in the woods. A lot of people die at you like that. All right, I just know it's not a way I want to go. I don't know, tiger or a shark? Which one would you rather?
I'd rather tiger.
I think probably tiger. I think a tiger's gonna like snap my neck, like, you know, Siegfried and Roy in about 2 seconds. So,
Well, I'd rather, if I were gonna be killed, I'd rather not be thrashing in the water, because I feel like that'd be also be drowning.
like
at
just
the same
eating
time.
parts off of you, maybe drowning at the same time.
Yeah.
And then like other fish are like coming to, they like smell blood.
As a lifeguard, I know drowning is my least favorite way of going out. I would hate that.
Tiger it is, people at home. All right,
There was some tiger in like India or Africa, I think. They like thought killed, like,
there aren't tigers in Africa.
Yeah, but they had like numbers of like people that killed like 1,000 or something.
I don't know about 1,000. I've heard of upwards of like in the hundreds in Bangladesh.
One they had like 600, and one in 1,000, I think.
People killed?
Yes.
I don't know about that. You're gonna have to look that up.
I didn't know there were no tigers in Africa.
Tigers are throughout like Southeast Asia. There are some lions in India still, and there used to be like cheetahs all throughout Asia, and lions also throughout that region, but somebody killed them all. That's right, people at home. Sensory adaptation. Read that one for us, Katie. I mean, do you sit around and think about your pants and your shirt being on all day? Your shoes being on?
No.
I mean, can you imagine being bombarded with that stimuli all the time? Like, oh, I feel my pants. Like, if you think about it, here, I feel my shoes are on, right? All you have to do is think about it. Like, are my shoes on? Yeah, I can feel it. But do you sit there and think about it all the time, even though you've got that stimuli of touch? Katie, are you going to read this or not?
Sensory adaptation. This is the decrease in a continuous stimuli coming in the CNS. This is what your brain does in regards to the constant detection of clothing on your body.
Yeah, so luckily our brains are smarter than the decisions we make sometimes. And so it's like, hey, we know there's clothes on there. You don't have to think about it all the time. Focus on important stuff. Types of sensory receptors. Interoreceptors are inside, detecting pressure, balance, homeostasis. You know, you eat too many refried beans, you get the bellyache, your stomach's like, gas is building up, Mason, you know what I'm talking about? Maybe not. And then you got that pressure inside, like how are you detecting that? So there are sensors throughout your body where you detect that pressure. We are going to talk about, ladies, the reproductive cycle and reproductive system and menstrual cycles before the 9 weeks is up. And so I'm sure, you know, at various times you can probably feel the effects of that. Or one day when y'all get to go into labor and you feel those internal pains hitting you. It's a beautiful thing. All right, exteroreceptors. These are sensory receptors on the outside. Mechanoreceptors are bending or stretching of hairs, so like mechanical. Nociceptors detect pain. Thermoceptors detect heat or cold, so you know you touch somebody, you can tell whether they're hot or cold. Chemoreceptors detect chemicals. This is like your nose and your taste buds, where you're actually taking chemicals in and you are determining what that chemical is. It's just like when somebody, let's say somebody's very flatulent and you smell it and you know you wish you had 3 more masks to put on. You know, I mean, essentially what's happening here is fecal matter has left their body. It's dispersed into the air. That fecal matter has made its way up into your nose, and you got a little patch of skin there called the olfactory epithelium on the inside. That fecal matter from their body makes its way, it dissolves in that patch of mucus and tissue up in there, and then your body's like, hey, you're smelling somebody else's feces. Do you ever think about that? You smell somebody else's feces, you basically got them in your nose. That's disturbing. Where was I going with that? Electromagnetic receptors detecting light. When we talk about our eyes. Electrical impulses. There are, what is it, like sharks or some fish can detect like electrical impulses in the water. I think one of those things they made for like great white sharks. I got a brother-in-law who lives out in California, likes to surf. And they make one of these things you can like wrap on your leg. And it's supposed to deter sharks from like coming up and biting your leg off, speaking of. And it sends out like an electrical impulse. So it's supposed to just to deter them. I don't know how effective it is, but they say it. I mean, if I were out there swimming around, I'd probably try it, to be honest with you. And then magnetic. I think of probably like animals that use the Earth's magnetic field to determine like migration patterns and stuff. I mean, like, how are those butterflies figuring out how to fly to Mexico and back to Michigan? I mean, come on, let's be honest. Most of y'all couldn't look at a map and make it from Mexico to Michigan and back, much less use the Earth's magnetic fields. I'd like to know how that works. All right, hearing. Let's go to a couple senses. The last two here are in your ear, literally. Oh, and there's another cool one here on 1105. You can see some hairs on insects that are used for touch. Beluga whales are thought to use the Earth's magnetic field. Pit vipers, like rattlesnakes. We've got quite a few pit vipers. What do they use? What's their special sense?
You know, like detect heat signature.
Yeah, they can detect heat in the middle, you know, when it's dark out. How many senses do we have as humans? You're a lively bunch. What are they, Mason? Smell, sight, taste, touch, hear. What's the other one? Balance. Equilibrium. So inside your ear, you have 2 sense organs essentially here. You have one for hearing and you have one for balance. The best, what is it called? The cochlea, sorry. The cochlea, the thing that looks like a snail there, and it's actually Latin for snail, that is where your hearing apparatus is. And basically inside both of these, you have a bunch of hairs that stick up, and then there's fluid in there. And when the cochlea, when you have sound that comes through, it hits your tympanic membrane, aka your eardrum. Sound then moves through, vibrates through those bones into the cochlea. And as that fluid vibrates, it creates, the hairs bend, it detects an action potential, or it causes an action potential, a stimuli, to go to the brain. And all you band people, you know, like pitch and tone and loudness, and what are some other qualities of sound? Whatever. So all of those things, like depending on how the hairs bend, our brain interprets that as a certain type, interprets it a certain way. Okay. And the same thing in the semicircular canals. There are 3 of them. So if you flip over to 1109, there's one that goes over the top, there's one that goes sideways, and then there's one at a diagonal. And the purpose of the semicircular canals, give me a second here, is if you got your eyes closed and you lean one way or the other, you can still keep your balance because you know where you are in relation to the earth, right? So it helps you maintain balance. So if you get an inner ear infection, it can disrupt the functionality of that. My mother had one and couldn't walk for 2 weeks one time. So, but it's the hairs you can see in that picture next to it. As the fluid moves over that, it causes those hairs to bend, and depending on how they bend, then our brain interprets that as movement. Now, I've heard of people who scuba dive at nighttime. They get disoriented, and if you're not careful, you can't tell which way is up because you really have nothing like that you're balancing on since you're floating. So you can get spun around in the water and be down in the water and not tell which way is up if it's completely dark outside. The only way you can really tell is to do what? Y'all are never going to make it. Blow bubbles. Yes, bubbles go up. And then I've also heard of the same thing when somebody gets caught in an avalanche and they're caught in an avalanche and tumbling down a hill and then they get covered in snow and it's all the same color around them and they're just packed in there. They can't tell which way is up. Even if they could dig a little bit, they couldn't figure out which way they're going. So the way you get out of that is to spit. And you spit, what's going to happen? It's going to go down. So then you tell your way up. Y'all need to get out more. All right, and then the last thing here, go back to the tympanic membrane since the other class talked about this. How many of y'all ever had tubes? Yeah, one of my kids had tubes. I forget which one. What's the purpose of the tubes in your ears? Y'all have kids one day and they probably had to have these. You might remember? They put tubes, they cut holes in your eardrums and they put tubes in there, like holes. Why do they do that?
Help you hear better.
It's not going to help you hear better because it's messing up your eardrum. It's ear infection. So when you're a baby, you know their heads are like kind of smushed together and their nose and ear. So basically what happens is there's no your ear drains kind of down this way. But when you're a baby, the hole in your ear that goes to the back of your throat goes kind of sideways. So if you're a baby sleeping and you have a sinus infection, what's going to happen? It's going to go out the back of your nose. It's going to drain down in your ear and go right down in there. And babies get ear infections and that pus builds up and their ears hurt and they cry all the time and they can't sleep through the night. Yeah, it's bad. So basically they put these if that happens a lot, they'll put those tubes in there. And so when they get an ear infection, it all drains out. And I remember my kids would just have white, crusty stuff all over their ears where that pus and stuff would drain out when they had an ear infection. And you still have to get antibiotics, but at least it relieved the pressure and released the amount of infection like that. And usually they'll fall out after, 2 or 3 years as you get bigger. And as your head goes up and your eustachian, your ear tube goes down, then that's not a big problem as you get older. Anyway, y'all have a good day.